Try a simple experiment right now. Close one eye and reach out to grab something on your desk. You'll probably notice something feels off. Your sense of distance becomes less accurate and your hand might miss slightly. This small moment actually explains a big idea. Depth perception matters more than we think, and it usually comes from having two eyes working together. Now imagine a robot trying to do the same thing. If it only has 2D vision, it can see objects, but only as flat images. It knows something is there, but it doesn't really understand how far away it is, or how to interact with it. That's why early robots often looked clumsy. They weren't just slow. They literally couldn't understand space. And this is exactly where 3D vision comes in. Its core purpose is to give machines the ability to perceive depth, to understand the world as something three-dimensional instead of flat. And once a machine can understand space, everything starts to change, from how it moves to how it grabs objects to how it navigates complex environments. Right now, the industry mainly relies on 3 different technical approaches. The first one is structured light, which works by projecting a known pattern onto an object and analyzing how that pattern deforms to calculate shape and depth. This method is extremely precise, especially at close range, which is why it's widely used in consumer devices like facial recognition systems, but it also has limitations because it can be sensitive to lighting conditions in more complex environments. The second approach is time of flight or TOF, which is more straightforward. It sends out a light signal and measures how long it takes to bounce back, using that time difference to calculate distance. This method is fast and works well in dynamic scenarios like obstacle avoidance in robots, but it may not capture fine details as accurately as structured light. The third approach is stereo vision, which mimics human eyesight by using 2 cameras to observe the same scene and calculate depth based on the difference between the 2 images. This method is relatively cost-effective and flexible, but it relies heavily on algorithms and can struggle in environments with low texture or repetitive patterns, so in reality there is no single perfect solution. Each method has its strengths and weaknesses and is suited for different use cases, and that's why many companies focus on specific directions instead of trying to dominate everything. When you look at applications, you start to realize how widespread 3D vision already is. Every time you unlock your phone with facial recognition, you are using it. When a robot vacuum navigates around furniture and avoids obstacles, it is relying on depth perception. In industrial settings, it becomes even more critical because machines need to measure positions, shapes, and even tiny defects with high precision. Without 3D vision, many forms of advanced automation simply wouldn't be possible. And then there's the growing wave of 3D scanning and 3D printing, where spatial data is the foundation of the foundation entire process. All of these use cases may seem different, but they share one common theme. Machines are evolving from simple tools into systems that can understand their environment, and this connects directly to a much bigger trend that people are talking about today, which is embodied AI. In the past, most AI lived inside screens, recommendation systems, or chat interfaces, but embodied AI is about intelligence interacting with the physical world, moving, manipulating, and responding in real environments. And the first step for that is perception. Machines need to see and understand before they can act. That's why 3D vision is often considered a foundational layer for the next generation of intelligent systems. And this is also why you see so much investment flowing into this space, not just from traditional vision companies, but also from chip makers, robotics firms, and large tech players, because once machines gain reliable spatial awareness, the range of possible applications expands dramatically. From simple automation to complex real-world interaction. Of course, the industry is still evolving, and there are still challenges to solve, things like performance, stability across different environments, cost control, and the integration between hardware and algorithms all take time to improve. But if you look at the long-term direction, the logic is quite clear. As more machines enter the real world and tasks become more complex, the demand for spatial understanding will only increase, not decrease. So you can think of 3D vision as a kind of underlying capability. It may not always be visible to end users, but it will be present in almost every intelligent system. And from an industry perspective, what's happening now is a gradual layering. Companies focus on core components like sensors and chips, others build complete systems, and some develop algorithms and software platforms. The real competitive advantage often comes from how well these pieces are integrated, especially for those who can combine hardware and software deeply. If You are looking at this space from a broader perspective. It's less about short-term hype and more about long-term positioning. This is not a field that matures overnight. Many technologies take years to move from lab to large-scale adoption, so instead of rushing to conclusions, it might be more useful to build a framework in your mind to understand where a company or a product sits in this ecosystem, what problem it is solving, and how far it is from real-world deployment. Once you have that perspective, you will start to see this industry much more clearly than most people.